Again, welcome to data mining course. In this lectures, we're going to discuss how we can use R to develop naive Bayes model, which is again a classification model. So here we say naive Bayes classification method are based on the Bayes theorem, which updates our knowledge about data parameters. So the concept here is probability, conditional probability concept. By combining our previous knowledge, which we call the prior distribution, with the new information obtained from observed data, this will result in updating the parameter knowledge called the posterior distribution. So again, the concept of naive Bayes is a conditional probability concept. So we start with the Bayes theorem. Here we are going to consider two predators, S1 and S2, and also a response variable of Y, which means the input of X1 and X2 will determine the output of Y, or the response variable Y, with three possible class values. So the Y can be Y1, Y2, Y3 based on S1 and S2 value. So our S1 and S2 is our predators, and our response variable is Y, which we have three possible class values. Now, the objective here is to identify which class is most likely for a particular combination of the predators X1 and X2. Now, Bayes' theorem will identify which class is the most likely by calculating the posterior probability for each of the Y1, Y2, and Y3. Also for the combination of the predators S1 and S2. And secondly, selecting the value of Y with the highest posterior probability. So let Y star be one of the three potential values of Y. Then the Bayes theorem said probability of Y equal to Y star given X star is equal to probability of X star given Y, which equal to Y star, times probability of Y given Y star, or probability of Y star, divided by probability of X star. So probability of Y equal to Y star is our prior probability. And then conditional probability with probability of X star given Y equal to Y star. So here we see how the data behave when the response variable is Y star. So conditional probability. Then probability of X star is how the data behaves without a reference to the response class, because this is X predators. So this will be our marginal probability. Now, probability that Y equal to Y star given X star will represent the formation or idea we have about how likely our class Y star is if we observe the particular predictor variables, values of X star. So probability of having one of the response variable output, Y star, given the predictor variables combination of the predictor variables values. So here there's no prior knowledge about the parameters. So we can use what we call the non-informative prior, which says that every class value is equally likely. So the maximal posterior hypothesis, here we say how to classify a record. So in our example, we have three possible values of Y star. That's Y1, Y2, Y3. And remember, Y is our response variable, which is the outcome. So for a value of X star, which is our predictor variables or the input variables, we calculate the Bayes theorem probability for the three possible values of Y. So the first one is, what is the probability that Y equal to Y1 given the predictor variables X is equal to probability of X star given Y equal to Y1 times probability of Y equal to Y1 all over probability of X star. Same thing applies to Y2. So here, our probability of S when Y is Y2. And probability of Y3 giving S also the same thing, probability of S star when Y equal to Y3 times Y equal to Y3. If it's Y2 times Y2, always divided by X star, the predators. So a maximum posterior hypothesis will tell us to classify the record X star as the value of Y, which has the highest posterior probability. So a class conditional independency, we said that if more than one predictor variable, then the class conditional independence assumption allows us to write probability of S star given Y equal to Y star as the product of independent events. So for the two predictor variables X star, we have X1 equal to Y1, S2 equal to S2. We can write that the probability of S star given Y equal to Y star as we have two predictors now. So S1 equal to S1 given Y equal to Y star times probability of S2 equal to S2 given Y equal to Y star. We will see the demonstration here. So for example, here we have a data set, which is 2 by 2 congested table. We have type red and white. The alcohol, the first column is high alcohol. Second column is low. Then the third column is the total. So you can see that here, the type red, the alcohol, high alcohol is 218, low is 282. So the total is 500. Same thing applies to the white, 268 and 232. Total is 500. So the total will give us 1,000. Same thing applies to the second. We have sugar high, sugar low, and the total, red and white. So our goal here is to predict whether the wine is red or white. Remember, this is our training data. We know how many is red, how many is white, based on their alcohol level, whether it's high or low, and the total. Same thing applies to the second way. We deal with the sugar level. If the sugar is high, this is what we have, low, this is what we have, and the total. So probability that our wine type will be red is 500 over 1,000, because when we look here, how many total red we have? 500. 500 total red, and the total wine is 1,000. So probability that our Y will be red is 500 divided by 1,000. Same thing applies to probability that our wine will be white. Still 500 over 1,000. So that's what we have here, red and white. So these are the two possible values of probability of Y. This we call the prior distribution of type. Now, alcohol flag has two levels. We have the distribution of the first predictor, P at X1. So here, P alcohol flag at high will be 486 by 1,000. And at low will be 514, 1,000. Again, we get this value from the data set based on the count. The total one is 1,000. So sugar flag again has two levels that make up the distribution of predictor variable P at S2. So we say the probability of sugar flag is high, is 416 by 1,000. If it's low, it's 584 by 1,000. Again, this 416 and 544 is given us in the data set. So conditional probability for alcohol flag and type. We say probability of alcohol flag is high, given the type to be red, to be 218 by 500, because the total red is 500. And alcohol flag for that category is 218. Now, when we are dealing with low, the total is 282. We need to get the total of 500. So 218 plus 282 gives us 500. So the same thing applies to the second. The data change now. The white is 268 for high type, and the low type is 232. So we can compare the prior probability of a 1 being read to the posterior probability of 1 being read, given its alcohol and sugar content are low. Now, probability of randomly selecting 1 being read is 50%. And when the one had a low alcohol and sugar, the probability of it being read 1 rose to 72.15%. And the data said that the red ones were more likely to be low in alcohol and sugar comparing to white one, based on the data values. So the naive Bayes in R, again, the same step as we did for decision trees. First, we need to load our data. Then when we load our data, the naive Bayes package for R is called E1071. So the package E1071 contains the naive Bayes classification algorithm. So first we need to store the E1071. Then we want to use it, so we use the library E1071. Then we are going to run, so that's our package again, E1071. As we said earlier, the whole concept is to understand or to know the package names. The steps are the same. First, load your data. Second, you can do data preparation. Third, apply your algorithm. By here now, first we need to get our package. So after that, we run the naive Bayes estimator. We are using the data. This time the data 1TR. So the formula, the type is alcohol frag plus sugar frag. And the data is 1TR. So the formula again takes the target variable type on the left of the table, and then the two predictor values on the right, which is alcohol and sugar level. Now, to observe the prior and conditional probability, we need to run the name of the model by itself. So here to be NB01. Remember, NB01 is our model. Now run the naive Bayes estimator. The model goes to NB01. Now we can predict the type of one using the predict command, same as what we went through with the cat. So here we have ypred. We use the method predict, then it takes the argument of the NB01, which will be our model, naive Bayes model. Then the new data will be data test. So we have the object NBO, the naive Bayes model, the new data equal to 1 test, the data set to use. So again, the steps are the same. First, we need to store the package E1071. We open it, library E1071. Then we run the naive Bayes estimator using our data set. This time we have to specify the predictor value and also the response. So that will be the conclusion of our lectures. Again, if you have any question, you can send an email or give me a call.